At the bottom of the Pacific Ocean, buried under sediment that hasn't moved in 2 million years, scientists found something that should not be there. Radioactive iron, not scattered randomly the way you'd expect cosmic debris to drift in over geological time, sitting in one single concentrated layer, a perfect band of material from a dead star. And when researchers looked closer, they found the exact same layer on the Moon, in Antarctic ice, across the Atlantic Ocean floor. Whatever delivered this material came from outside our solar system. It came at one specific moment in time, and it got through something that was specifically designed by nature to stop it. The protective bubble that surrounds our entire solar system, the thing that has been shielding Earth from the violence of deep space for billions of years, was compressed so completely that every single planet, including Earth, was left sitting naked in interstellar space, unprotected, exposed. And while that was happening, our ancestors were just beginning to walk upright on a cooling Earth whose climate was shifting in ways that may never have been fully explained. Until now. This is not ancient history. The evidence is sitting in the ground beneath your feet right now. And what scientists discovered in 2024 and 2025 has changed everything we thought we understood about how safe we actually are out here. To understand what happened 2 million years ago, you first need to understand what normally protects us. Because most people think the solar system ends somewhere around Neptune, the last planet, and beyond that, there's just empty space until you hit another star. That picture is completely wrong. The sun doesn't just sit still and shine, it breathes. In every direction, simultaneously and constantly, the sun exhales a stream of charged particles called the solar wind. Protons, electrons, and alpha particles, traveling outward at speeds between 400 and 800 kilometers per second. That stream doesn't stop at Neptune. It doesn't stop at Pluto. It keeps going for hundreds of billions of kilometers, pushing outward against the material that fills the space between star systems. That material, the diffuse gas and magnetic fields drifting through the galaxy between the stars, is called the interstellar medium. The pressure of the solar wind pushing outward against the interstellar medium, pushing inward, carves out an enormous bubble. And everything inside that bubble, every planet, every moon, every spacecraft we've ever launched, every human being who has ever lived, exists within it. That bubble is called the heliosphere. It is the closest thing our solar system has to a skin, and its job is to filter. The interstellar medium is not friendly. It carries galactic cosmic rays, high-energy particles accelerated by supernova explosions across the galaxy, along with radioactive isotopes and radiation that can alter chemistry and damage DNA. Most of that material never gets anywhere near Earth because the heliosphere deflects or absorbs it, long before it penetrates to the inner solar system. Scientists think the heliosphere is one of the primary reasons life on Earth was able to develop the way it did. It's a layered defense system. The heliosphere stops most of what's out there. Earth's magnetic field stops most of what gets through the heliosphere. Earth's atmosphere stops most of what gets through the magnetic field. 3 nested shields, each one catching what the last one missed. The outer edge of the heliosphere, the line where the sun's influence ends and true interstellar space begins, is called the heliopause. For most of human history, it was entirely theoretical. Nobody had ever been there. Then, in August 2012, Voyager 1 crossed it at approximately 121 astronomical units from the Sun. That's about 18 billion kilometers, roughly 3 times the distance from the Sun to Pluto. Voyager 2 followed in November 2018. For the first time in history, humanity had instruments on the other side of the heliosphere, sampling what interstellar space actually feels like up close. The plasma beyond the boundary was colder and denser than the plasma inside, exactly as predicted. The magnetic field just beyond the heliopause ran parallel to the field inside, which nobody had expected and which still puzzles researchers today. But there is something deeply important that scientists still don't agree on. Nobody knows what shape the heliosphere actually is. For decades, the textbook image showed it as a comet shape, a rounded nose on the side facing the direction the sun moves through the galaxy, and a long trailing tail stretching out behind for thousands of astronomical units. It feels intuitive. A moving object pushing against a medium should pile up at the front and stream out behind, the way water piles against the bow of a ship and streams past the stern. But an astrophysicist at Boston University named Merav Ofer has spent years building detailed models that challenge this picture entirely. In her models, the heliosphere doesn't have a long comet tail at all. Instead, the rear of the bubble deflates and forms 2 curling jets at the poles, folding back on themselves. Her team describes it as a deflated croissant shape. The tail, in this model, essentially doesn't exist. This debate is not academic. The shape of the heliosphere determines where its walls are thinnest, it determines where coverage is weakest, and it determines how quickly the entire structure can change if something presses against it from the outside. 2 million years ago, something did exactly that. And what it did to Earth is only now becoming clear. The interstellar medium is not uniform. Between the stars, the gas and dust and magnetic fields that fill the galaxy are clumped and layered, with colder, denser regions moving through space on their own independent trajectories. The Sun currently sits inside one of these structures called the local interstellar cloud, a wisp of warm, partially ionized gas. That cloud is itself embedded inside a much larger, much emptier region called the local bubble, which was carved out by a series of nearby supernova explosions over the past 10 to 20 million years. But the Sun isn't sitting still inside all of this. It orbits the center of the Milky Way at approximately 220 kilometers per second, completing one full lap every 230 million years. The entire solar system travels with it, and that journey takes the Sun through regions of the galaxy with very different densities and compositions. Most of the time, the heliosphere handles whatever it encounters. The solar wind pushes out hard enough to hold the boundary steady, and the interstellar material flows around it. But the galaxy is constantly shifting, and not everything in the Sun's path is gentle. In 2024, Merav Ofer and her collaborators published a paper in Nature Astronomy that did something extraordinary. They traced the Sun's position through space, not forward into the future, but backward, 2 million years into the past, using computer models built from decades of heliospheric data. They mapped precisely where the solar system was sitting at the moment those radioactive iron deposits were being laid down in the ocean sediment, and what they found in the neighborhood stopped the field in its tracks. In the region the Sun was passing through 2 million years ago, there is a structure called the local ribbon of cold clouds, a long chain of dense, cold hydrogen clouds drifting through the interstellar medium. One cloud in particular, which researchers named the Local Lynx Cloud, appears to have been moving on a trajectory that would have brought it into direct collision with the heliosphere at almost exactly the same moment the iron deposits were being laid down. The timing matches almost perfectly. Ofer's team ran simulations of what that collision would have looked like. The results are genuinely difficult to absorb. The heliosphere, which normally extends to roughly 100 astronomical units in the direction the Sun is moving, remember, Earth orbits at just 1 astronomical unit from the Sun, was compressed dramatically. The simulations show it was squeezed down to approximately 0.22 astronomical units, less than a quarter of the distance between the Earth and the Sun. The entire protective bubble of the solar system, the shield that has been keeping the worst of the galaxy at bay for billions of years, was pushed inward past every planet, past Mars, past Venus, all the way down toward the innermost solar system. Every planet, including Earth, was briefly sitting outside the heliosphere, exposed directly to the interstellar medium with no protection whatsoever. Picture a bubble being crushed between two hands until it's barely the size of a golf ball. Everything that was inside it is now sitting in the open air. That is roughly the scale of what the simulations describe. And everything that the heliosphere normally blocks, galactic cosmic rays, high-energy radiation, the particle debris of long-dead stars, streamed freely through the space where Earth was orbiting. Among that flood of particles was iron-60, a radioactive isotope of iron produced only in the hearts of dying stars, in the nuclear furnaces of supernova explosions. It cannot be made on Earth. It cannot be produced by any natural geological process on our planet. Its presence in concentrated layers on the ocean floor, on the moon, and in Antarctic ice is not ambiguous. It came from outside. It came through the window the compressed heliosphere left open, and it settled into the sediment while our ancestors were just learning to walk upright. The evidence for this has been assembled from multiple independent sources over several decades, and the convergence of all those separate lines of evidence is what makes the case so powerful. The most widely cited confirmation comes from a 2016 paper in Nature by Anton Wallner and his colleagues, who analyzed ocean sediment samples and found concentrated iron-60 deposits clustering with remarkable precision around a window of roughly 2 to 3 million years ago, with the strongest signal right around 2 million years ago. Earlier work in 2004 by Klaus Knie and collaborators used iron-manganese crusts pulled from the Pacific seafloor. The same chemical fingerprint appears on ocean floors across both the Pacific and Atlantic, in lunar samples returned by the Apollo missions, and in ice cores drilled from Antarctica. Every independent measurement points to the same window of time. Every independent measurement tells the same story. And iron-60 has a specific property that makes it an unusually reliable clock. It decays at a steady, known rate with a half-life of 2.6 million years. This means that for iron-60 to still be detectable in sediment layers 2 million years old, it had to have arrived approximately at that time. If it had been deposited earlier, it would have decayed beyond detection. The presence of measurable iron-60 in layers 2 million years old is not just evidence of an event. It is a timestamp. That timestamp lines up with something else. The same period, roughly 2.58 million years ago, marks the formal beginning of the Pleistocene epoch, the long cyclic era of ice ages that shaped the world our ancestors evolved in. Average global temperatures dropped, ice sheets expanded, the climate of Earth shifted in ways that drove evolutionary pressure across every species on the planet, and it was in the same window that the earliest members of the genus Homo appeared in East Africa. The direct ancestors of every human being alive today emerged during a period of global cooling that began right around the time the heliosphere was being compressed and the interstellar medium was reaching the inner solar system unfiltered. Whether those events are causally connected, whether the cloud encounter triggered the cooling, contributed to it, or simply coincided with it, is exactly what researchers are working to establish right now. Ofer herself was direct about what her paper demonstrated. She described it as the first study to quantitatively show that there was an encounter between the Sun and something outside the solar system that would have affected Earth's climate. Brian Fields at the University of Illinois, one of the scientists who first proposed a supernova origin for the iron-60 deposits back in the 1990s, called the work interesting and provocative while noting that important questions about the precise timing and the causal chain remain open. The core finding is not in dispute. The heliosphere can be overwhelmed. It has been overwhelmed. The evidence has been sitting in the ground beneath our feet the entire time. Now here is where the story gets even stranger. Because while all of this was being established about what happened 2 million years ago, something else was discovered at the outer edge of the solar system that fundamentally changes how scientists think about what is out there right now. On May 21st, 2025, the International Astronomical Union's Minor Planet Center made an announcement that received almost no attention outside specialist circles. A team of researchers led by Sihao Cheng at the Institute for Advanced Study in Princeton confirmed the existence of a previously unknown object at the edge of the solar system. They called it 2017 OF201, and what they found is one of the most extreme objects ever recorded in our solar system. At the time of discovery, this object was sitting approximately 90 astronomical units from the Sun, well beyond the heliopause in the region where the Voyager probes are now drifting. Its closest approach to the Sun, called its perihelion, is about 44.5 astronomical units, roughly comparable to Pluto's distance. But its farthest point, called its aphelion, stretches to more than 1,600 astronomical units from the Sun. And its orbital period, the time it takes to complete one single loop around the Sun, is approximately 25,000 years. The last time this object was at its closest point to our star, modern humans had not yet left Africa. To picture that orbit in physical terms, if you compress the entire distance from the Sun to Neptune into the length of a football pitch, the far end of this object's orbit would be sitting roughly 3 kilometers away, somewhere past the car park and down the road. It is an orbit so stretched, so elongated that the object spends the vast majority of its existence in the frozen dark, far beyond anything any telescope we have ever built could detect. The researchers estimate it is only within observable range for approximately 1% of its total orbital journey. We caught it in that 1% window almost by accident, sifting through old survey images with computational tools sophisticated enough to connect faint dots across years of archived data. Its estimated diameter is around 700 kilometers, calculated from its brightness and assumed surface reflectivity. At that size, gravity pulls a body into a roughly spherical shape. That is one of the criteria for dwarf planet classification, the same category as Pluto. If the size estimate holds up, it would be the second largest known object in its particular dynamical population, the class of bodies with extremely wide detached orbits that barely interact with Neptune at all. How did it get there? The researchers are direct about this. An orbit this extreme doesn't happen in one step. It requires at least one close encounter with a giant planet, something that slingshots an object outward onto a much wider path. But the scale of this object's aphelion suggests the process went even further than a simple slingshot. Chung and his colleagues believe it was flung all the way out to the Oort Cloud. The Oort Cloud. This is the structure at the very edge of everything we consider our solar system. It is not a disk like the asteroid belt or the Kuiper belt. It is an enormous spherical shell of icy debris wrapped entirely around the solar system in every direction. A deep freeze time capsule holding leftover material from the solar system's formation 4.6 billion years ago. It is predicted to begin somewhere around 2,000 astronomical units from the Sun and extend outward to perhaps 100,000 astronomical units, roughly halfway to the nearest star. Nobody has ever directly observed it. It is theoretical, inferred from the behavior of the long-period comets that occasionally fall inward toward the Sun on trajectories that can only originate from that far out. At those distances, the Sun's gravitational grip is so weak that even small external nudges can disrupt the orbit of anything sitting out there. a passing star drifting through the galactic neighborhood, the slow tidal pull of the galaxy itself. Any of these can reach into the Oort Cloud and redirect objects inward. Scientists believe this is the mechanism that sends long-period comets on their plunges toward the inner solar system, disturbed from their frozen parking places by gravitational influences from beyond the solar system, and sent falling inward on journeys that take thousands of years. In the case of 2017 OF201, that is apparently what happened. It went out to the Oort Cloud, spent time in the deep cold at the edge of interstellar space, picked up whatever it encountered out there, and came back on a journey measured in geological epochs. The discovery also complicates something that has been debated for years in planetary science. For a while now, the primary observational argument for an undiscovered large planet in the outer solar system, the hypothetical object called Planet 9, has rested on the apparent clustering of extreme trans-Neptunian objects around similar orbital orientations, as if something massive were gravitationally herding them into alignment. But 2017 of 201 does not follow that clustering. Its orbit points in a completely different direction, deviating from the pattern that the Planet 9 hypothesis was built to explain. The researchers note this directly. It doesn't kill the idea outright, but every new extreme object that fails to fit the predicted clustering makes the hypothesis harder to defend. What the discovery does confirm is that the region beyond the Kuiper Belt is nowhere near as empty as it appears. Chung's team estimates that if an object of this size exists in this population, there are likely hundreds of similar objects sharing comparable orbits, all of them currently too faint and too far away for any existing telescope survey to detect. Objects that have been thrown to the edges of the solar system, some of them possibly out to interstellar space and back, carrying in their composition and their orbital histories a record of the gravitational violence that shaped this neighborhood over billions of years. Right now, approximately 1 million miles from Earth in the direction of the Sun, a spacecraft is collecting data that did not exist 6 months ago. NASA's Interstellar Mapping and Acceleration Probe, called IMAP, launched on September 24, 2025. It spent its first month traveling to its observational position at the first Sun-Earth Lagrange point, called L1, a gravitationally stable location that gives it an uninterrupted view of the Sun. IMAP arrived at L1 on January 10, 2026. By February 1st, all 10 of its instruments had recorded their first measurements, and its 2-year primary science mission was officially underway. What IMAP is doing has never been accomplished before at this level of detail. It is mapping the heliosphere's boundaries from the inside by detecting energetic neutral atoms, particles that form at the heliopause when charged solar wind ions collide with neutral interstellar gas, become electrically neutral in the process, and stream back freely toward the inner solar system unaffected by magnetic fields. Because these particles travel in straight lines, the pattern of where they come from reflects the shape and structure of the boundary where they originated. 3 of IMAP's instruments are designed specifically to catch these particles across a wide energy range and build the first genuinely detailed portrait of what the heliosphere actually looks like from the inside. That portrait matters enormously in light of everything the cold cloud story established. The shape of the heliosphere determines where its walls are thinnest, how much interstellar material leaks through under normal conditions, and how quickly the entire structure can be overwhelmed if something dense enough pushes against it from outside. A croissant-shaped heliosphere with 2 curling polar jets behaves completely differently under compression than a comet-shaped one with a long, trailing tail. Knowing the real shape for the first time gives researchers the ability to model future cloud encounters with genuine precision. Within IMAP's 2-year primary mission window, the debate between the 2 heliosphere shape models that has divided the field for years should finally have observational data sharp enough to settle it definitively. Meanwhile, Ofer's team is already pushing the research further. Using data from the European Space Agency's Gaia mission, which is building the largest 3-dimensional map of the galaxy ever constructed, they are tracing the Sun's trajectory backward, not just 2 million years, but 7 million years, looking for other dense cloud encounters in Earth's deeper past. If the Lynx cloud encounter happened once, there's no reason to assume it was the only time. The Sun has been orbiting the galaxy for 4.5 billion years, moving through regions of vastly varying density. The cold cloud structures that compressed the heliosphere 2 million years ago are not unique features. The question of how often this has happened, and what each encounter did to Earth's climate and its developing biology, is one that Gaia's precision mapping may help answer in the coming years. At the outer edge of the solar system, the Vera C. Rubin Observatory in Chile, designed to survey the entire southern sky repeatedly with unprecedented depth, is expected to start revealing the hidden population of extreme objects like 2017 OF201 as its data accumulates. Every new discovery will either tighten or loosen the case for Planet 9 and will add another data point to the picture of how the outer solar system was shaped by the gravitational chaos of its earliest history. And out beyond everything we have mapped, beyond the Kuiper Belt and the scattered disk and the inner Oort Cloud, in the space where even our most distant spacecraft are only now beginning to reach, there's a frozen archive of everything that has ever happened in this corner of the galaxy. Objects that have been to the edge of the solar system and back, objects that may have briefly entered interstellar space, objects carrying chemical signatures from the formation of the solar system 4.6 billion years ago, locked in ice that has never been warmed by sunlight. A record so old and so complete that reading it properly could tell us not just what happened 2 million years ago, but what has happened dozens or hundreds of times over the entire history of complex life on Earth. The outer solar system is not a quiet boundary. It is a crossroads. It is a library. And we are only just learning how to read what it wrote. The iron at the bottom of the ocean didn't arrive randomly. It arrived during a window when the thing built to stop it had been overwhelmed. It settled into sediment. It settled onto the moon. It fell into ice on Antarctica and waited there for 2 million years while our species evolved, built civilizations, launched spacecraft, and eventually drilled down and found it. That iron traveled further than anything we have ever built. It crossed interstellar space. It passed through the gap left by a compressed heliosphere, and it came to rest in the ground beneath our feet. We didn't know any of that until very recently. We are still working out what it means. And the most unsettling part of all of this is not what happened 2 million years ago. It is the question nobody wants to ask directly. If the heliosphere was overwhelmed once, compressed down past every planet, leaving Earth exposed in the open interstellar medium, what is stopping it from happening again? The answer is nothing. Nothing at all. Only the question of when.